Hello, everybody. I'm Jags Ram Narayan. Let me start by first apologizing for Barzan. Turns out he's not here. Turns out he's going to be a father literally this week, so he's not here. We're very happy for him. So let me start by first talking about who we are. So SnappyData is a we like to call ourselves as a Spark-based startup. It's been around for roughly just 6 months. It was incubated actually in Pivotal, which itself is a spin-out from EMC and VMware. We've been building essentially a fusion of an in-memory database that we built over a decade with, it's deployed with hundreds of accounts globally. That engine's focus was all transactions running in distributed main memory, sort of a traditional distributed system, right? A clustering system that's really focused on consistency and replication consistency. And we are trying to fuse that with Spark into a single cluster. And I'll go through some of those ideas here. About 25 engineers, just 6 months old, right? So here is the brief agenda. I would like to motivate you folks on what we consider as sort of this emerging need for mixed workloads. And by mixed workloads, we mean workloads that involve streaming, transactions, essentially mutating things, and we also need OLAP queries, all in a single sort of application. And the classic answer is Lambda. We think it's relatively complex, and I'll sort of motivate you on like why we think there is complexity involved. We'll then touch on state management, essentially how, given Lambda, how do you manage Lambda managing state today? We'll touch on the inefficiencies in that state management. Then I'll lead to some of our ideas, sort of with Snappy in a sort of a single unified cluster. I'll also touch on sort of this topic that I think is going to disrupt at some point being able to work with relatively large data sets, which is this whole field of approximate query processing. Those of you who know BlinkDB would have gotten some exposure to approximate query processing. We're incorporating approximate query processing at a very real-time streaming level itself. And then if time permits, I will essentially go through some of the design ideas we've essentially incorporated into Snappy. So why is mixed workloads increasingly common? Here's a simple example with manufacturing IoT or a sort of industrial IoT. We're looking at a stream, a very large stream coming out from a windmill farm, and it's going through a processing pipeline ending up in probably Hadoop or data lake, right, on which you run interactive analytical queries. The classic pipeline till date has typically been very simplistic analysis, right? For instance, here you might be mapping sensors to tags, you might be looking at temperature. If the temperature is above or below a threshold, you want to send an alert. All possible with just traditional simplistic CEP solutions itself. But increasingly, I think the processing is shifting into something more complex, right, where you want to potentially correlate a temperature from the last 2 minutes and look at what did I see from a trending standpoint yesterday, day before, sort of similar time periods in the past, which requires joins, complex things. Or more increasingly, you might want to do interesting things like, score a model, right, essentially in fact, even build a predictive model on the fly. And finally, even the data lands up in my store, I want to run OLAP-like interactive queries. So it does look complex, right? I mean, you're looking at sort of enrichment in the first phase that requires potentially pulling data from a reference data, could be an Oracle, SQL, MySQL, what have you. Then data in motion analytics. As I'm going through the stream, I'm looking at state, how do I manage state in a mutating way? And what we're frequently finding is that as things become a little bit more complex, given all these failure conditions, it's not just enough to say I can manage a counter. You typically have to very frequently land up in situations where multiple counters need to be updated, and given failure conditions in modern day systems, all of a sudden you could have consistency loss. So transactional semantics all of a sudden becomes very interesting and important. Joins to history, trends, and finally, of course, once the data has landed in my landing zone, not just historical, not just that, I'm sort of meandering my way through HDFS, through a SQL on top of HDFS, where all of a sudden you have dealing with stale data and you're running OLAP queries. Can I now run my OLAP queries on my real-time state and include my history when I run my OLAP queries? So what we see today with the sort of, maybe there are 5 products in the stack, right? Maybe probably a lot more, right? The complexity involved is pretty high. Now, there is a whole bunch of subjective complexity involved, which I'm not going to get into, right? Disparate APIs, you have to master multiple, tuning options, you have to configure multiple products. So it's complex. The total cost of ownership is high. it's actually slower, wasted resources, right? So the question is, can we simplify and optimize? This is the fundamental question we're trying to answer, to say, can there be a single cluster that operates like a database, except it also gives you entire Spark functionality, something that can manage state, can do transactional workloads, and can also run OLAP queries. So with that, let me just get into a little bit into Spark from a managing state standpoint, right? So if you look at here is another example for ad impression analytics. An ad impression, for those of you who don't know, is anytime you see an ad, not necessarily you haven't clicked it, you saw an ad on a web page, that counts as 1 impression per user. So if you have an ad service that's managing, let's say, ads across a whole bunch of sites, you can easily imagine that now all of a sudden an AdAnalytics service is dealing with hundreds of thousands of events every second, right? Those of you know AdAnalytics are pretty familiar with this sort of domain. And this is the classic Kafka, right? Okay, let's getting into Kafka, ingest my impression logs, going through a Spark streaming cluster, and I might be working with one or more data stores in the process, right? And the application quite often essentially has to sort of stitch things together. Maybe I have to run a query that has to combine data from NoSQL store and combine it with something that comes from a SQL store. So the point on this slide is that given that we are trying to ingest a lot, right? I'm simply trying to say that how about a simple example that says I want to pre-aggregate some of this data, otherwise I'm dealing with terabytes every few hours potentially, right? So I'm trying to pre-aggregate so that we can reduce the data set, and that's what I want to ingest. So I'm saying that let's pre-aggregate the data as it's streaming in based on publisher and geography. So let's look at what happens in this write path by looking at a simple piece of Spark code. I mean, this deliberately I said, okay, let's actually imagine how it would be with Spark 2.0 and Kafka streaming, right? So it's using the new continuous data frames or infinite data frames or whatever you want to call it, right? I mean, the structured streaming thing. It's very beautiful now because now all of a sudden I can essentially operate with much simpler APIs, much easier to reason with than D streams, and I can use stream and say, hey, I essentially get a continuously emitted data frame that I can operate with. Given that it's a data frame, I can use all the data frame APIs at my disposal, right? So doing a group by is relatively straightforward. The very nice thing that those of you attended the talks earlier today, Spark now will essentially offer windowing as if it's a function for grouping data, which makes it really easy too. And then finally, I'm saying, listen, I'm going to take my pre-aggregated data. After I've done this reduction, I'm going to shuffle it and write it to my favorite NoSQL database, right? Now, those of you know anything in Spark, I mean, you know one thing, right? Shuffle lands up to be the most expensive thing if you're doing anything essentially real time. And it typically, you could easily land up in a situation where you're throttling your upstream sort of feed, if you may, right? And the second thing is that not only do you have that expense of shuffling inside the Spark cluster, if you're writing it to my NoSQL data store, the NoSQL data store typically has its own data formats. It has to go through its own serialization sort of machinery. It will redistribute data. Maybe it has a replica that it has to distribute it to. So you really are looking at, well, shuffle is expensive, and the shuffle is expensive for not just the fact that it uses a shared file system, but also for the fact that pipelining is kind of restrictive, right, somewhat, because the stage has to completely finish before the next stage kind of begins. So as this pipelining becomes more incremental in nature, I think shuffle starts to improve too. The other thing that got missed out very often, what you see on the right-hand side here, is simply the excessive copying that happens in modern-day Java-based systems. And all I'm showing here is, let's say I'm writing to a data store that is replicating for HA, right? Could be any of the favorite NoSQL data stores. And if it's a Java-based system, you're looking at, 10 copies before I give it a single object, and it has to replicate, right? And in our sort of big data kind of systems, especially if you look at Spark and Spark streaming, we are essentially writing batches and micro batches at all times, which means the cost of copying you really need to pay attention to that, right? So in this simple example, you're talking about a network to a kernel, to a user space in the Java young generation, probably to a from the to space to the older generation, right? And then I have to replicate, so I have to make, again, a copy from the user space back to the kernel space to the network buffer. I literally replicate that on my replica, and an ACK comes back. So you're looking at, 10, maybe 12 copies. And you add HDFS or Hadoop into the mix, you're probably looking at 20 copies of data, right? So one way you could avoid this bottleneck is to say, hey, how can I localize my state, right? So all I'm showing here is to say, hey, in my case, if I am aggregating data based on publisher and geography, how about a partitioning strategy that everybody in the pipeline shares the same partitioning strategy? Obviously, you'll only realize it in some situations. Some situations, you just can't, right? The business requirements are such that you cannot really partition it that way. So the idea here is that if there was a way to tell my key value store, my NoSQL store, saying use the same partitioning as the upstream partitions in Spark, and also the same upstream partitions in Kafka, all of a sudden you could potentially localize my state and you're avoiding unnecessary shuffling, at least on the ingestion side of things, right? Not always possible. Now let's look at, well, is that so that's obviously a nice big leap, right? I mean, we avoid the shuffle and at least avoid the serialization and copying costs. But is there an impedance mismatch with key value stores? Right? I mean, if you look at by and large every streaming thing out there, I mean, today, we all land up talking about these NoSQL stores to write. And they all happen to be key value store, except that I also laid out saying, once I've ingested, what do I want to do? I want to run OLAP queries, right? And what does an OLAP query look like? I mean, here is a simple example. A couple of examples. I want to find total uniques for ads grouped on geography. Well, what does that look like? I mean, that query looks like a group by query where I have to scan essentially every single record. Essentially now if you look at sort of the state of the art with databases today, you have two choices, right? You have a row-oriented store, you have column-oriented store. The row-oriented stores are really great for fast key-based lookups, but relatively very slow for aggregations. And if you look at a column-oriented store, great for aggregations, but relatively it's very difficult to do updates, especially random updates. And the row-oriented stores also consume a lot more memory, right? Oh. Excuse me, guys. Oh, this is not good, huh? Should I send it? Don't send. I apologize, guys. You would think that, okay, there you go. All right. I think Microsoft didn't like that slide, maybe. For some reason, it only happens when I play the deck. I mean, if I'm not playing, it's all good. Uh-oh. Fingers crossed. Okay, thank you. All right, so this slide is, so most of you probably recognize that, hey, a column-oriented store is better when it comes to analytics, right? But why so? And this slide is pretty telling, right? What this is simply depicting is that if you go back to the 80s, CPU, essentially accessing a random memory location was roughly 6 clock cycles, 10 clock cycles. Today, there's a huge delta between modern day CPU speeds and still DRAM speeds, right? Even though they're kind of catching up with a variety of new DRAMs technology, it still takes about a whopping 150 clock cycles, probably much more depending on what you're trying to do, right? So that's the single biggest reason why it's very important to say, if I'm doing a scan, if stuff is in contiguous memory, I automatically get advantage of the L1, L2, and L3 caches in modern day CPUs, right? So anyway, so the question is, hey, is a column-oriented store really fast enough? Right, here is a simple example that says, I'm doing a count star, group by, an order by, and a limit, right? Absolutely as simple as it gets. Still, in our, we're just running it to Spark. Everything is sitting in, the executor memory. In this case, we were roughly using, I believe, about 12 cores out of the 32 cores available just to run the query. And still takes a whopping 10 seconds, a single user, a single query. This is really interactive speeds, right? Can we get to Google-like interactive speeds for some of these exploratory analytics? That's a question. So that's why, for us, it's relatively important to say, can we use statistical techniques and probabilistic data structures to dramatically shrink the data essentially available? So for instance, today, if you were, most apps would be happy to trade off a 1% accuracy for a 200x speed up, right? If I can say, if you look at the visualization on the right, it's essentially taking, 2 billion data points and essentially visualizing a map here, right? Took 71 seconds with this visualization environment, hitting a database. And with some of the sampling-based techniques, it takes about 3 seconds, right? And it looks pretty much the same. So in some sense, we are saying that often you can make perfectly accurate decisions with imperfect answers. Okay, so with that, let me just jump into SnappyData. It is an open source project. You can check it out on GitHub. love for folks to participate in our community. It's a fairly new approach. It is an approach where we're essentially, like I said before, we're taking what we built over about a decade or so, an in-memory database, essentially with Gemfire, a low latency, a traditional replication-driven HA design, high concurrency, and essentially sort of fused it, if you may, with Spark. And there are all sorts of details on what kinds of extensions we did to Spark and all that, so we can get into that. But the idea here is that, one thing to always remember is Spark is fault tolerant, not highly available, and there's a big difference between the two, right? Which does matter when it comes to real-time applications. So anyway, it's a single cluster. That's sort of the design center for us. So what do we get at a high level? We get row-oriented store. That's why you can do point lookups, indexing. You can essentially easily execute essentially mutable operations. You can execute a transaction, indexing. All that comes from sort of what we got from Gemfire. We had our ODBC, JDBC in a REST way to submit essentially even Spark jobs. And then we are completely fully capitalizing on the Spark engine. So in a way I look at it as, to us, in this environment, Spark and Spark programs is a new stored procedure for us, right? So it's almost like you write your Spark program, whatever it is, right? Use the rich libraries and you submit and we run it, right? And of course, we're dependent on the columnar formats that we manage in our column tables. It's exactly the same as how Spark, if you go on cache or persist, is the same format we use. We, of course, land up essentially allowing mutable operations on column stores too. And of course, everything is given that Spark works with Hadoop really, really well. A little bit more of marketing here, right? It's 100% compatible with Spark. A number of extensions, transactions. We also implemented the first sort of version of saying, if I want to do stream processing purely using SQL, could I do that? And then when it comes to the store itself, while we have these storage models with row-oriented and column-oriented formats, we also support not just saying, given a data set, I can partition and scatter it across a whole bunch of executors, but we can also essentially say you can replicate data sets, right? You can essentially create n replicas of any piece of data which could in fact be mutating. And the beauty of that is often we still end up saying, whenever I'm analyzing, it's a star schema. I'm doing a star schema join, and I have my code tables all sitting as replicas, much more easier. On the approximate query processing side, these are the common techniques, right? Uniform random sampling. Probably a lot of you are familiar with using sampling techniques to dramatically reduce a data set, and I can ask some question, I can get a response back. The question really becomes like, with uniform random sampling, how good are my answers going to be, right? It's very easy with uniform random sampling to miss out on, subgroups that are very rare, right? In my example, if I have a geography that is a very rare geography, has very low representation in the full data set, and I land up doing a random sample, I'll miss that data. So we are heavily dependent on sort of at least stratified sampling with a bunch of variants on stratified sampling, something that BlinkDB originally did also. Then we're also supporting essentially several techniques to say, how do you deal with outliers? How do I deal with a question that says, give me a top K of something, right? So probably some of you are familiar with the count-min sketch as a probabilistic data structure. So you're sort of taking count-min sketch and said, how can we take count-min sketch and apply it to time series data as an example, right? Because that's one of those challenges with these data structures, that while they can dramatically decrease your footprint and can answer questions quickly, most of these data structures are built such that the questions you can ask is one and only one, right? So how do you essentially allow time series data to be managed with the count-min sketch is something we've been looking at. We're looking at other techniques for outlier management and detection. And one of the things we are kind of big on is to say, why not degrade the value of data over time, right? So exponentially decaying, essentially. So if I'm managing an infinite stream, and that infinite stream is so large, right? I want to manage the next 10 years of the data, can essentially degrade the quality of data in some sense, right? Exponentially. So here is another interesting graph. It's essentially showing that when my sample is very small, my error rate is going to be pretty high, right? But as my sample size starts to grow, there is a point where, in other words, the error rate starts to exponentially taper off, fall down, and there is a point at which, you don't really need to grow your sample anymore. Your error rate is low enough, right? And even if you double the sample, the error doesn't change all that much. That's kind of what it's depicting. So the beauty of this is you might be dealing with 100 gigabytes of data, and you need 20 gigabytes in your sample. You might be dealing with a terabyte of data. You still might need only 30 gigabytes or 40 gigabytes in your sample. So let me just quickly switch to, I was just going to show a demo. All right, assuming this works. Okay, so I mean, this is just, I'm just going to rush through it, given that I have like, I guess, 10 minutes. I guess everybody knows Zeppelin notebook. So I'm just using the airline Ontime data from the Department of Transportation. I mean, essentially the airline, the flight performance data. So what we're going to do is we're going to manage the data in exact form as well as our stratified sample. Both of the data sets are available essentially as tables. So if you look at this straight up Spark code, much like any other vendor, we essentially extend SQL context, not Spark context, we extend SQL context called Snappy context. That's pretty much the only difference. Everything else is just straight up Spark, right? So I'm loading up my Parquet data, and I'm registering that, the full data set as a table, a temporary table called Airline. Then I create essentially a single stratified sample, which is also again registered as a table, right? So I'm creating a sample table called Airline sample, and the fraction is 1%. I have a reservoir. I mean, we actually do, first we do reservoir-based sampling, followed by essentially how we keep it in our stratas. So I'm creating a 1% sample, right? And then I have another table, which is a reference data table, so I can do a join, right? Oh, this is, let me just actually, oops. Well, I was going to show things side by side. Maybe it will still work. Okay, there you go. All right. So what you see on the left is really running a query on the exact data. Everything on the right is queries on the stratified samples, right? So if you look at this, it's got about 210 million records. If I run the same query on airline sample, it comes up with 99.99% correct answer, even though the sample is 1%, about 2 million, right? So if you look at these queries now, I'm just running straight up simple, which airlines has the most flights, right? The query on the left and the query on the right is nearly the same with one difference, right? We essentially added this with error clause with 0.1. And you use that is enough of a hint to say, yeah, I'm okay, I can tolerate a 10% error in my answer. The moment you give that sort of hint to us, we'll automatically figure out and say, hey, can I use a stratified sample as if it was an index, and I can return an answer back. So if you look at this, I actually ran a whole bunch of queries concurrently. That's why it is, if you look at the left, it took about 126 seconds, right? On the right, it took literally 2 seconds, right? And on. I mean, I have a whole bunch of examples like that. Which airlines arrive on schedule, 111 seconds. And if you look at the results, I mean, this is almost, in this case at least, given the stratas I've used, you can barely tell the difference, right? You can barely tell the difference that, in fact, they're not exactly identical, but they're nearly identical, right? So it really works really well for a number of scenarios like this, right? I mean, here is another. So one of the other thing is, like in this, so stratified sampling, some of these techniques are relatively easy. What is really difficult is, and almost to me at least feels like rocket science, is the ability to compute an error relatively very accurately, right? Where I cannot really look at the full data set to compute an error. I got to just look at the sample and still compute an error with a very, very high confidence, right? So I mean, we have simple functions that are built in, like absolute error, relative error, things like that, that you can use inside a query, so that not only can I fetch my answer, I can say, hey, give me my actual error that you guys computed, right? So you can essentially decide whether you want to consume an answer or throw it away, right? So okay, I'm going to switch back now. All right, so just revisiting that AdAnalytics example. So I mean, this is kind of what it looks like inside the executive JVM, right? I mean, we have the column tables, the row tables. Anything is visible as a SQL table, or if you love Spark, you want to look at it as a data frame, you can just simply look at it as a data frame. It's just transposable, right? And then, of course, an approximate query processing data structures are also looking at as tables, right? So the idea here, to some degree, is to sort of say, in this design, can I think about almost like a new analytics cache-like pattern, right? Where this analytics cache is built using Spark streaming, and it can manage streams, it can manage my state, right, my windows, but not just windows, reference data, and essentially my last n minutes, right, and whatever that n is, depending on the budget you have, in all in main memory, everything's sitting in Hadoop or Hive or what have you, right? And then I can also summarize my data for significantly longer periods using approximate query processing techniques, right? Stratified samples or what have you. And then, of course, I can, given row tables or what have you, you can essentially synchronously maintain a reference data, which basically means if, let's say, in my AdAnalytics example, my CRM data is changing, well, guess what? I don't have to refresh that CRM tables entirely. You can just continue to update as and when those tables change, right? All data is visible as data frames. I touched on that, right? So anyway, and the final point is, anytime you're running an OLAP query, the engine would figure out how to federate the query, right? How to figure out saying, can I essentially look at the cache and can I satisfy an OLAP query? That's very different than traditional caching techniques where given a key, of course, I can figure out whether the cache has it or not, right? Very different than that. So here is, here's vendor speak, right? So we did a benchmark. I mean, this is all available. If you look at the link at the bottom, you can download the benchmark code. It's all out there. So we did this first thing to say, hey, if my traditional Lambda is using Cassandra and I'm concurrently ingesting and querying, what do I see, right? This is simply saying on the concurrent ingest side, with about, I guess we had 4 instances of C4 2x on AWS. We're doing about 700,000. This is only utilizing some number of cores. I'm not sure how much out of the available 32 cores for that ingestion. And we were using Kafka in asynchronous mode, otherwise Kafka wouldn't keep up at all. Anyway, so all this code is out there. Cassandra was, because again, as I said, it has to serialize copy, into the Cassandra JVM, so you pay a price, much slower, and we also compared it to an in-memory, a commercial in-memory database also. On the querying side, while I'm ingesting, I'm also running OLAP queries. I'm just giving you one example here of the OLAP query, but there are several other queries we're running, and we do much better in that performance. So how did we extend Spark? I'll just give a 1-minute thing. I'll stop, take your questions, right? I can't really get into details here. I don't have the time. But one sort of, from a design standpoint, it is rather quite interesting and challenging to take a lineage-based system for fault recovery and take a traditional distributed system that's based on group membership and consensus protocols and sort of fuse them together, right? I mean, sort of that's kind of what we landed up doing. So in that process, I mean, there are a number of things that just probably you would also recognize, right? One is that in sort of Spark world, I mean, if you submit your application, you get your context, it spins up your own set of executors, which is great for a batch environment. But for us, it is like saying, hey, here is a database that's up and running, and I cannot have separate database instances so that I can run a query every single time. I mean, the whole idea is to say, can it be a shared database? Can I essentially look at the same data, allow multiple users to come in and look at it? And of course, you have security. So if you want to essentially prevent users from doing wrong things, you have security. So essentially, we make these executor JVMs long-lived. That's one fundamental thing. We also essentially sort of say the Spark context and the driver itself is managed, because if the Spark driver goes away, the executors go away, right? In our case, we couldn't do that. So we had to extend the cluster manager and all that. So in a nutshell, I mean, I guess Spark executors are long-running. Driver failures don't shut down executors. Even if a driver fails, what we have is this lead node that's essentially running. There can be multiple lead nodes. They're all essentially connected in an HA-like configuration, right, using our clustering system underneath the covers, which means if the driver goes away, we can immediately detect and say, hey, secondary, take over. I mean, it's not fully baked. I mean, there are still kinks to be worked out. And to do that, we had to essentially extend the Spark's cluster manager also, at least a standalone cluster manager quite extensively. So anyway, so the HA, and then of course the data itself is HA. Very, very, very big difference, right? It's like saying, hey, when my stream started to emit data and I wrote a batch out to my store, it's immediately replicating at this point, right? So it's almost like saying my checkpoint is every time I write. And we do bypass the scheduler for low latency SQL. So anytime I'm doing there's no point if I'm saying, hey, Bob, get me my record, right? Get me Bob's record. Why am I involving the scheduler? That's like hundreds of milliseconds of overhead and all that. So we look at a query and say, is this query a really low latency query? It's not as simple. It's simply going after row tables. We sort of look at things differently today. But the idea is to bypass the scheduler completely for low latency SQL. We did a number of optimizations on top of Spark Catalyst, given that we could do replicated tables, we could do co-location, stuff like that. Okay. So with that, let me just take some questions. Oh, by the way, we have an event at, if you guys really want to get into it, we're happy to talk. We are trying to build a community. It is an open source project. We have an event today at this place called Tradition at 7:30, right after the sort of the mix and mingle here in Spark. So if you're interested, please, it's just about a block away, is my understanding. Right. So thank you very much. Happy to take questions.